This is section 15.5 on directional derivatives and the gradient. The gradient is a big deal. The gradient is one of the main 3 or 4 things in this class that are a big deal and that we finally get to do it. So this is great. We will end up defining the gradient based on the idea of the directional derivative. So there's a lot going on in this section. It's got 6 objectives. The first 3 are basically, what is a directional derivative? What does it mean graphically? Can you write down a definition of it? And can you actually compute them? Then the other 3 are all about gradients. Can you explain what they mean graphically? Can you figure out what they do, like how they operate, what are their properties? And can you compute them and draw pictures of them? I just want to point back at the exact sequence that is supposedly going to be a big deal in that, like, it's going to be a summary of a lot of the things that happen in this class. What we've got here is functions. This C infinity R3R is functions that have an input as points in space. And their output is individual numbers. If you take the gradient, that's this arrow, the word over the arrow there is grad. If you take the gradient of a function, you get this kind of object, and that object is a vector field. This is big news because we won't even officially bring up vector fields, but they've been kind of floating over my head for the whole class so far. And technically, when you take the gradient of a function, you get a vector field. Now, we'll kind of shy away from that mostly, but as long as you can keep straight the fact that we've got like functions and we're taking the gradient of those functions and we're getting some other new object, you'll be fine for now. But this section is up there as far as importance is concerned. So let's jump into it. Cool. So first, let's get a nice picture of what partial derivatives were. Directional derivatives are supposed to be an extension of that. So the idea of a partial derivative was you've got some surface. I don't know, it looks like this maybe. You've got some surface, you pick a point on the surface, and you say, well, what's the slope at that point? And when I ask what's the slope at that point, the only thing you can really answer is like, well, what do you mean? I mean, you could come at that point in the x direction and find the slope when you're moving in the x direction, or you could come at the point from the y direction. And you usually get different slopes depending on those different perspectives. If you're on the side of a hill, well, one way is up, it's very sloped, and the other direction is flat. You'll stay at the same height no matter which direction you go. So the partial derivative, let's write something down. So the partial derivative of a function with respect to x was, oh, it's written right here, was the slope of the surface in the positive x direction. This was partial f partial x, and in the positive y direction. I don't like putting that there. Okay, yeah, partial f partial x was the slope in the x direction. And partial f partial y was the slope in the positive y direction. Let me look back at my notes here because I think I want to put the vector in here. Let me just make sure. Yeah. So the x partial derivative was saying, well, how about you go in the direction 1, 0? And the y partial derivative was saying, how about you go in the direction 0, 1? So it gives you like a direction to look while you're standing on the surface. Say like, look east and tell me what the slope is. Is it going up or is it going down? And then this other one says, look north. And then you find the slope looking in that direction. The point of this section is like, wait a minute, what's so special about the x direction and the y direction? Why not pick some other direction? Why not go northeast? Why not go north-northeast? How about 2 degrees west of south? There's infinitely many different directions. We shouldn't be locked into just these 2 partial derivatives. So if you think of that, then this is called the directional derivative. The path of this section is we'll first say, okay, let's figure out what the directional derivative is as a formula first. And then when we get through the end of the formula, we'll realize that there's this thing that keeps showing up, and then we'll name it, and it'll be called the gradient. Yeah. Okay, so let's build the definition first. So first, let's pick a direction. The easiest, like most standard way to write a direction is to give a unit vector, because we think of vectors as having magnitude and direction. If you take away a vector's magnitude by making it a unit vector, so it's length 1, then we think of it as being a direction. Unit vectors all look like this. Unit vectors in the plane. So let me change my data type up over my head. Unit vectors in the plane, you just pick an angle, and you go in the direction cosine theta, sine theta. That's a 2-dimensional vector. Just like saying northeast is a 2-dimensional direction. It tells us the direction to look and try to figure out the slope of the surface in that direction. So if we're given a unit vector and a point, let's say we know the x and the y, and then the z, I guess I'll say that the z comes from a function f of x, y. On the surface, we can create the equation of the line in the xy plane through our xy point, and go in the direction of this unit vector. I don't want to write this again, so I'm just going to name it u. Generally, we'll use u for a vector if it's a unit vector. So it's just, like, you don't have to, but the context matters. Like, you'd use p for a prime number or n for an integer. You use u for a unit vector. Okay, so we're trying to find the slope of a surface in this weird direction u, and our plan is going to be to draw the line in the xy plane that goes in that direction, and then use that line. So let's get the line first. What is this x and y? Oh, yeah, okay. So we're starting at x0, y0, and we're going in the direction. So we're starting at x0, y0, and we're going in the direction cosine theta, sine theta. So x starts at x0 and goes up at a rate of cosine theta. And y starts at y0 and goes up at a rate of sine theta. This is a line in the xy plane that goes through x0, y0. Okay, now we'll just look at the part of the surface that's up above that line. So all of the points will look like, they'll still look like x, y, f of xy. But you can always like connect that point with the base point that we actually care about, which we called x0, y0, f of x0, y0. I don't know if you can imagine this, but we'll get, for each point on the line, we'll get a secant line that's in the correct direction. This says maple animation. I don't have a maple animation. It's too bad. see if I can get it on the picture that we had before. Not really. Maybe if I draw a simpler one. So let's say you have this point here. The point is x0, y0, and then f of x0, y0. And you decide that you want to know the slope in this weird direction u. That looks like I'm pointing straight up. I want to go like, instead of going north or west or something, I want to go like in this weird direction. To do that, I go down to the xy plane, get that vector u, and then I built a line that goes in that direction. And then I go up onto the surface, and I get this part of the surface that's going in that direction. The same way that I have these like paths that go in the x direction or the y direction, well, now I'll go in the u direction. Then if I get some point on this line, well, the point on this line, I can go up to the surface, and the base point also goes up to the surface. And the last thing that I said was that you would get a secant line, and that's the line between our base point and this point. The idea here is that this line up here on the surface is getting at the slope that we're interested in. So let's get the formula. Let's write the slope of the secant line first. So this is the secant line's slope. We need rise over run. Okay, well, the y values are just written here, not the y values. The heights are just written here. So the difference in the heights is the rise. And then the run is like how far over you go. Well, that how much we go over is all based in the xy plane. So that's the distance between xy and x0, y0. Okay, this is quite a mess, but x and y have nice formulas here. This x0 plus, like the x and y come from this line. And we made the line out of cosine theta and sine theta. So something not so bad will happen. In particular, in the denominator, x minus x0, well, x minus x0, if you take away the x0, all that's left is cosine theta t. And y minus y0, same deal. All that's left is sine theta t. The numerator, I mean, whatever, it's a mess. So let's just leave it how it is for now. So what happens down here in the denominator? Well, I can factor out t squared, so I'll get the square root of t squared. And then I'll have cosine squared plus sine squared of theta. So this denominator just has a t in it. So the end result of what's left is that I'll define this to be called the directional derivative in the direction u. Just let t go to 0. The denominator simplifies to t. The numerator, I mean, all I can really do to reduce the number of variables is just write x and y in terms of like the theta that we had before. So this would be x was x0 plus t cosine theta, and y was y0 plus t sine theta. x0, y0 have no simpler form. So this is our formula for the directional derivative of a function in the direction u. Now, will you ever have to do this calculation that I did up above? No. The point is that if you write your direction as a unit vector u in terms of theta, that the formula comes out nice because of this cosine squared and sine squared. So maybe this doesn't look nice to you, but it's nicer than it could be. One more thing is this weird notation. We had f sub x or f sub y for the x partial derivative or the y partial derivative of f. Here, we don't write f sub u. Instead, we say capital D sub u. And this means so the capital D is derivative. So it's the derivative of f. But then the u is a modifier on D. So it's the u derivative of f. So it's the directional derivative of f in the direction u. That's what this says. And then there's this crazy formula here. The limit doesn't always exist. Sometimes you'll have like a cusp on your surface or something that'll stop the limit from existing. But if the limit exists, this is what the derivative is. Okay, this formula, not good, not fun. I don't want to deal with this formula if I can avoid it. Luckily, we can avoid this formula most of the time. So the time that we can avoid it is, well, as long as z itself, as long as this function f of xy has all the types of derivatives, it has both partial derivatives, x and y, then actually it will turn out that this simplifies like this. That you get fx times cosine theta plus fy times sine theta. Now, these are two formulas for the exact same thing. This formula up in the lighter box, we built from first principles. I picked out a direction, I put a line on the ground, I sent the line back up and found a line between those 2 points and found the slope of it. It was kind of complicated, but we built it from scratch. This we have not built from scratch yet, but this formula looks way better. We want to use this one instead. In order to make it okay for us to use this way easier formula, we need to provide what is the connection between these two things. So let's see it. It's a proof of this theorem. This theorem's pretty useful. It means you can find the slope of a surface in any direction by just first finding the slope in the x direction and then in the y direction. To do this proof, what we'll do is we'll recognize that it kind of looks like almost everything in here is really a constant. The thing that's really the variable here is t. So why does that happen? Well, when we're trying to find the directional derivative of a function, what we do is we're going to do that at a specific point. So we fix a point x0, y0, we decide that in advance. And then we also decide in advance a specific direction that we're looking for the directional derivative. So that's choosing the unit vector u. And when we choose that unit vector u, that also fixes theta, because u is cosine theta, sine theta. So we want to try to think about this as a function of t. Now, there's t's all over the place, so it's kind of a big mess. So let's just name this whole function in terms of, let's name this new way of thinking about the function f. So let's let g of t be f of x, y, where we realize finally that x is really just being decided by t and y is being decided by t. Okay, if this is what g is, then what is our definition here in the white box? Definition is that duf is the limit as t approaches 0 of, okay, we got some stuff here. This is g of what specifically? I guess this is g with just a t plugged in, because it's literally f of x, y. And then over here, this is g, but with a specific t plugged in, namely t equals 0. And this is all divided by t. Okay, now what is this? The limit as t approaches 0 of g of t minus g of 0 all over t. That, from Calc 1, is what the derivative of g is at this point, at the point 0. So this is g prime of 0. This is kind of a surprise, that actually by changing our perspective of this big ugly thing being like a function of lots of variables into being a function of just t, we're able to notice that this directional derivative is actually just a regular old single variable derivative if we think about it the right way. Okay, so this is g prime of 0. Just to be a little more suggestive about it, I'm going to write this as dg dt at t equals 0. The reason is we just finished the chain rule, and there's a reason we just finished the chain rule. This function g, it actually depends on x and y, and x and y depend on t. So if anyone ever needs dg dt for any reason whatsoever, the chain rule tells us how to find that. There's two paths. You take the path through x, and you take the path through y, and you add them together. Now, what are x and y actually? X and y are these things, this like x naught plus t cosine theta and so on. So let's just copy it down here. Writing it under myself is not clever. We'll copy it here, that x is x naught plus t cosine theta, and y is y naught plus t sine theta. Okay, so now let's find all these things and see what happens. Well, partial g, partial x. Oh, g is f. Okay, so this is partial f, partial x. There must have been a better way to write this. G was just like our nice name when we were thinking of g as a function of t, but like g is defined to be equal to f. So if you're trying to find partial g, partial x, you should go back and look like, oh, right, g was made out of just the function f. Okay, we don't have any inside information about f, so this partial f, partial x is just going to have to stay. The nicest way I have to write it is f sub x. The nicest way I have to write partial f, partial y is f sub y. Now we need to find dx dt and dy dt. Well, dx dt I can find by just using the formula for what x is. The derivative of x with respect to t, well, derivative of x naught is 0, and cosine theta is a constant. So we're just taking the derivative of a constant times t. That's the constant. Similarly, dy dt here is 0 plus sine theta. So what happened by us just taking our ugly looking formula, realizing that it was really a function of time, so that we could get everything to look like a derivative, and then applying the chain rule allowed us to get the ugly looking formula to turn into this nice formula, which is the one that you'll actually use. So that's our nice formula for the directional derivative of f in the direction u. Let's do an example to just see what it, see how it works. Let me get the formula written here. So the question says, here's a surface, here's a base point, and here's a direction. So there's like a mountain, and a place to stand on the mountain, and a direction to look. And the question is, what's the slope in that direction? If the direction was directly in the x direction, or directly in the y direction, you'd just do a partial derivative. But here, because the direction is 30 degrees north of east, that's not a partial derivative, that's a directional derivative. So we use this formula. So we need to find f sub x. Well, f sub x is the x partial derivative of the function. Cosine theta? Well, theta is apparently pi over 6. F sub y? Well, I can take the y partial derivative. Sine theta? Well, theta is pi over 6. Now we're trying to find the directional derivative of f in the direction u at a specific point. So we actually know x and y also. So this is 3 times 1 times 9. And cosine of pi over 6 is just a number, root 3 over 2. X cubed is minus 1, y is 3, and sine of pi over 6 is a half. So this directional derivative is just, it turns out not to be so bad. It's 27 halves root 3 minus 3. The main way that this formula can go wrong is that it has a lot of letters and a lot of different variables that are all in different states of being variables or constants. The way that you handle this is by writing every step and just writing things that are equal to each other directly under each other. So I wrote out the formula, and then I thought about f sub x, and I didn't think about anything else until I was done with f sub x, and then I moved on to the next thing. If you try to keep too much of this all in your head at the same time, it's just too many variables, and it's just not a recipe for success. But if you just write the formula and then translate the formula into what you know, then it's just not hard. Okay, let's do the same surface. It was f equals x cubed y squared. The base point is going to be 2, 1. And the direction is going to be in the direction minus 1, 2. Now, that minus 1, 2 is not a unit vector. So I need to get it down to being a unit vector before I can call it u and say the directional derivative in the direction u. So let's get a picture of this in the xy plane. In the xy plane, it goes mostly, it's like north-northwest. It's this direction. The unit vector in the same direction will be the same thing but scaled down. This vector has a magnitude of square root of 5, so we'll need to scale it down by the square root of 5. And in particular, once you've scaled it down to be a unit vector, what you've got is cosine theta and sine theta. So when you pull out the formula, which is that the directional derivative in the direction u is fx cosine theta plus fy sine theta. Well, I've got cosine theta and sine theta ready because I've got a unit vector. Fx and fy, well, I'll have to do a little bit of partial derivative action, but most of the work is done. So fx is 3x squared y squared. Cosine theta. Fy is 2x cubed y. And then I have a sine theta. And then I can plug in all these things. So x is 2. Y is 1. Cosine theta is minus 1 over root 5. X is 2. Y is 1. And sine theta is 2 over root 5. these are going to be like terms, so we will combine them. This one is minus 12 over root 5, and the second one is 1632 over root 5. So I end up with 20 over root 5. Small thing is that you can break up 5 into 2 copies of root 5. So like 20, I'm going to split up as 4 times 5. And then 5, I can split up as 2 copies of the square root of 5. And the reason that's useful is if you ever need to cancel a square root of 5. Like you can always break a 5 into 2 square roots of 5. So we can get this answer to look pretty nice. 4 square root of 5. Cool. Okay. I think we'll end this video pretty quickly here, but the trick here is that if u is just in the x direction, then what will happen? If u is just in the x direction, then the angle we're looking at is the angle 0. And in that case, cosine theta is 1 and sine theta is 0. So if you try to take the directional derivative in the x direction, you shouldn't use the directional derivative formula because the directional derivative in the x direction already has a name. It's called the partial derivative in the x direction. But if you forget and you use the formula, then you'll go through all this, and then you'll do fx times cosine theta plus fy times sine theta, and you'll get fx. You'll go, aha, the directional derivative in the x direction is called fx. Like, yes, it is. If you instead go in the y direction, in the direction j, well, the direction j has angle pi over 2, so you'll get cosine theta is 0 and sine theta is 1. And then when you apply the formula for the directional derivative, you'll get fx times 0 plus fy times 1, and so you will still get the y partial derivative as you should. I'll break the video here into 2 parts just because this section's really long, but that's directional derivatives in all different directions. There was a bunch of proof in here, and you don't need to reproduce the proof, but you should try to follow these things so that it doesn't feel like math formulas fall from the sky. And then the formula that you actually use that you need to be really comfortable with is this one, that the partial derivative in the direction u, which is a unit vector, is fx cosine theta plus fy sine theta. All set.